In this video, I'll be performing a normal modes analysis using Pshells and cylindrical coordinates. Full details of this exercise are on page 400 of the PDF linked in the video description below. I'll first start Patran, and I'll create a Patran database called prob16. The units for this example are in inches, pounds, and PSI. I'll click OK here on the right. I'll create a curve, and the radius of this round surface is 4. So type in 4 for the X, start from the origin, and then I'll make a second curve that is 2 inches in length. And if I scroll over here, you'll see the first curve that has a length of 4, and if I am careful with the mouse, I can find the second curve here. Or to better do this, I can go to label control, turn on the curve number, and here you see when I hover over the 2 or the middle of the entity, it automatically highlights that entity. And same thing for the other curve. Now I have to rotate these about the z-axis so I can create my surface. So under geometry, go to surfaces, revolve, create surface revolve. The total angle of rotation is 360 degrees, and this will rotate about the third axis of coordinate system 0, which is the z-axis. I'll select this curve, and that is my surface here. Next, I'll select surface or curve 2. Since auto execute is on, it will automatically create my next surface as soon as I click another entity. Before moving on, I'll create my cylindrical coordinate system using the 3-point method. So here, select type cylindrical, accept the defaults, and hit apply. And now you can see my new coordinate system. Under properties, go to isotropic. For material name, call it matte. For input properties, under elastic modulus, type in 1E7. For your Poisson ratio, it's 0.3. Your Poisson or your density is 0.00026. Hit OK and click apply to make this material. Under 2D properties, click shell, call this prop, change standard formulation to P formulation. Under input properties, select the material we just made. Under thickness, type in 0.25 inches, click OK. For your application region, select this surface, click add, OK, and apply. Under loads BCs, we'll define element uniform displacement. We'll call this support. Our target element type is 2D. My input data will have an edge translation restriction of 0, 0, 0 for the X, Y, and Z. For analysis coordinate frame 1. Or this is not X, Y, and Z. This is actually 1, 2, and 3 in coordinate system 1, which is cylindrical. Click OK. For my application region, I'll simply select this outer edge. Add, OK, and apply. Going on to meshing. For my mesh seed, I'll define a requirement of 12 elements for the outer curve and the inner curve. Once my mesh seed is done, I'll select the surface mesher, switch this to Tria, make the topology Tria 13, select this surface, surface 1, and hit apply. I have to go ahead and equivalence this, click equivalence, and hit apply. See the pink markers indicating where duplicate nodes have been deleted. I could then analyze this by going to the Analysis tab, analyze the entire model. Under solution type, switch this from a linear static analysis to a normal modes analysis. Under solution parameters, we'll switch the output format from XDB to OP2. Click OK and hit OK here. OK here. Go into subcases. Select this default subcase. Under subcase parameters, type in number of desired roots 15, or normalization method is maximum. Hit OK and apply. Click cancel and hit apply to analyze this. Under OP2, I can import the OP2 results. If I look at my results, I see I get a value of 726 Hertz, 2031, 3700, 4300, and so on. And when I compare this to the values I should get, I am close to the values. And the last time this was performed, they obtained the same values I just showed you. To view the modes, you can go to Quick Plot Fringe, select this first one, select this fringe result, select this deformation result, and click Apply. You can see the mode shape here. If I select this next result, I can view this mode shape. And if the mesh is obscuring the view, I can go to Fringe Attributes, or I should go to Deform Attributes and uncheck Show Undeform. So when I hit Apply after that, that disappears. If I wish to see the mesh on the actual mode shape, I can go back to Fringe Attributes. Under Display, select Element Edges and hit Apply. Now you see the mesh on the mode shape. And I can do this for the other frequencies. And you can see that they actually compare to what they show in the example here. And the last one is 10,000 Hertz. Let me clean this up. And one last comment. If I look at the coordinate system the nodes are using, they're using the global coordinate system. I can modify them to use the cylindrical system as shown here. Go to Modify, Object is Node, Method is Edit, check these two, select this coordinate system for both, pick all the nodes, hit Apply. When I reanalyze this, I'll call this one _2, hit Apply. When I reanalyze this, I should obtain the same results. So when I import the OP2 file, go to my results, you'll notice that 1, it kept the old results, and 2, the new results are at the bottom. And here you can see that I get the same values when I switch the coordinate frames. And for simplicity, I'll just review the last one. So this is the one using cylindrical coordinates, and this is the one using the global system here. And I obtain the same mode shapes and frequencies. You can clean it up, save, and this concludes this example.